Hey everyone, Mr. Skelton here, back at it for, this is going to be the video for lessons 1 and 2, you can see on the screen there. And what we're going to do is, really, we're going to be reviewing some of the stuff that we learned in geometry. So we're starting our unit basically on trigonometry. E-T-R-Y, okay? Trigonometry. Now, when you say trigonometry, I know that's a loaded word. Trig is triangle. Metry means measure. And so if you just break down the word trigonometry, it just means triangle measurements. All right? And so we're going to start with the trig that we're doing. It's going to be right triangle trig. Okay? So I'm going to put right triangle trig. And so when we talk about right triangle trig, the first thing we're going to review real quick is just Pythagorean theorem. All right? And so I'm going to just hand draw a right triangle as best I can. And I'm going to use some numbers that are common. This is called a Pythagorean triple, not that you need to know that, but a 3, 4, 5 right triangle. Now the reason it's a 3, 4, 5 right triangle, and I know those to be true, is because I can just take 3 squared plus 4 squared equals 5 squared. Right? Your hypotenuse is always the longest side, and so that's a squared plus b squared equals c squared. We get 9 plus 16 equaling 25, and we get 25 equaling 25. So those numbers all check out, and that's a right triangle. And I'm going to refer to this triangle, and I may draw it again when we start to do some of our trig ratios. Without going and reviewing all of your geometry skills from your trig units that you did sine, cosine, and tangent with, basically what we're going to talk about today are some core functions of trigonometry. Specifically speaking, we're going to talk about sine, which we use sin, cosine, which we use cos, and tangent, which we use tan. Okay, and those are the abbreviations there on the right. So sine, cos, and tan, and we're going to talk about those here in a second. And really what these are, sine, cosine, and tangent, just for review purposes, what are sine, cosine, and tangent? They represent ratios. What are ratios? Remember, ratio is just fancy word for fractions. Okay, they represent ratios of the sides of the right triangle. And that's what we're going to focus on to get that in there. Okay, so sine, cosine, and tangent, they represent fractions or ratios of the right triangle. So this first slide that you have here that says special right triangles, we're actually going to skip and come back to that. So I'm going to turn the page, and we're going to focus on this second slide right here as it comes into focus. And we're going to review those trig ratios, okay? And so I'm going to put my little right angle right here, and I'm going to do 3, 4, and 5. And we already talked about that 3, 4, 5 right triangle. And obviously there are other numbers that can work for a right triangle. And we're going to talk about our sine, cosine, and tangent ratios. Now, the ratios themselves are right here. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Now, a couple things let's get to clarify here. I'm going to try to give you as much review as I can without going too crazy here. This is theta, and theta represents an angle. So when you see this symbol, this is the theta symbol, it just represents an angle measure. Okay? And so I'm going to put a theta symbol right here. And that just means we're talking about that angle. So the sine of this angle theta is opposite over hypotenuse. That ratio remains the same. You probably remember from geometry something like this. SOHCAHTOA, right? SOHCAHTOA, you may have had a geometry teacher that gave you some story about, an Indian Native American princess named SOHCAHTOA and blah, 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 blah. So SOHCAHTOA. S is sine, which is opposite over hypotenuse. Cosine, you don't have to write this out. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Okay? And that's what they mean. Now, in terms of Everybody knows usually what the hypotenuse is. The hypotenuse is always the longest side, and it's always opposite the right angle. When I taught geometry, I would put a little tail on the end here, and I would say the right angle kind of makes an arrow. Do you see the arrow there with the right angle? It always points to the hypotenuse. In terms of your adjacent and opposite side, your adjacent and opposite side vary depending on where theta is or what angle you're talking about. For example, if I want to find, now that I have angle measures, or excuse me, side lengths, let's actually write these out. Let's do sine of theta. So what would be sine of theta? Well, here's theta right here. We know sine is opposite over hypotenuse. So what side is opposite of theta? It's 3. That would be the opposite side. The hypotenuse is 5. So for this theta, the ratio is 3/5. Let's do cosine. Cosine of theta. Well, what's cosine of theta? Here's theta. Cosine is adjacent. So when I say adjacent, I always say the side that is touching theta, that's not the hypotenuse. So obviously this angle measure is formed by this segment and this bottom segment. Obviously 5 is the hypotenuse, so 4 would be the adjacent side. The hypotenuse would still be 5, so 4/5 would be the ratio there. And then finally tangent. Tangent of theta. Here's theta. Tangent stands for opposite over adjacent, so opposite over the adjacent side, 4, would be 3/4. Okay? Now, let's just say, for the sake of another example here, let's put theta, let's put another angle measure, we'll call that theta there, and I'll do it, I'm probably doing this a little bit backwards, I'll do it in pencil. So let's talk about theta here. If I said sine of theta, and I'm referring to this theta now, well, what's sine? Sine is opposite over hypotenuse. So what's the opposite side of this angle? 4 would be the opposite side. 3 would be the adjacent side, 4 would be the opposite side, and 5 is always the hypotenuse. So that would be 4/5. Cosine of theta would be adjacent over hypotenuse, which is 3/5. And tangent of theta is going to be adjacent, or excuse me, opposite 4 over adjacent 3. So 4/3. Okay? And so that's just some real basic trig ratios that are always going to hold true. So hopefully you can remember SOHCAHTOA, and hopefully you remember just some basic values or ratios from right triangles. All right? We're going to use these in some of the examples here in a little bit. All right, let's go back to the front page. Because we're going to get into some more specifics and a little bit more detail and difficultiness, or more difficult problems when we get into our unit circle and some of the other trig that we're going to do in Algebra 2, we want to pay special attention to our special right triangles. And you also learn this in geometry, but I want to take some time to review. So, you may or may not remember, because we didn't spend a ton of time, on our 30, 60, 90 right triangles. So there's my 90. I'll put my 30 degrees here. I'll put my 60 degrees here. And what we're going to do is we're going to talk about the relationships with the sides, and I'm going to prove this to you, so give me a little bit of your time here. Lightly in pencil, I'm going to kind of connect and make this triangle. It's probably a little too big. Doesn't have to be perfect. That looks a little better. And I'm going to put a 60 degree here, okay? And I'm going to put another 30 here. So I basically put a congruent triangle to this gray one on the other side. And if you look at the big picture here, you'll see a 60 degree angle, 60 degree angle, 60 degree angle. So I have an equal angular triangle, which means all the sides are equal, right? Equal angular, equilateral. And what I'm going to do is I'm going to call this side 1. So if that's 1, that means that's 1 here, which means an entire side would be 2. And you can pick other numbers, but for the sake of the ratios that we're going to create that you probably remember from geometry, I'm using a 1. So let's think through this. If this entire length is 2, 1 from here to here, 1 from here to here, the other sides all have to be 2. 1 plus 1 would be 2, then 2, then 2, because again, 60, 60, 60, equal angular, 2, 2, 2, equilateral. So if this is 2 here, let's find this side length right here using Pythagorean theorem. So that would be 1 squared plus, I'll call it x. X squared equals 2 squared. So that's 1 plus x squared equals 4. x squared equals 3, square root, x equals the square root of 3. So this right here is now the square root of 3. Okay, I'm going to erase everything but that. Okay? On any 30, 60, 90 right triangle, the sides have these ratios to them. Okay? Now you may remember in your 30, 60, 90 work something like this. The long leg is always the side opposite the 60. So your long leg, I used to call it LL, is always radical, or is always your short leg times radical 3. And your hypotenuse is always 2 times your short leg. Okay, those were the equations you learned in geometry. And so we get these equations from this. Here's your short leg, which is 1, right? Your hypotenuse is always 2 times your short. Well, what's 2 times 1? It's 2, right? Your long leg, which is this opposite of the 60 degrees. So when I say short and long, short leg, long leg. Long leg, because 60 is bigger than 30, your long leg is always opposite the 60. Your short leg is always opposite the 30 because 30 is a smaller angle, thus opposite shorter side. So those are the two equations you used in geometry to find your long leg and short leg. All right. Over here on the 45, 45, 90, I'm going to kind of do the same thing. On a 45, 45, 90, this is actually an isosceles triangle, right? Because you have two angles that are congruent. So these legs, we call these legs, those have to be congruent. So again, I'm going to just use 1 because it's a good length to use. And then we're going to find the hypotenuse. I'll call it x. So 1 squared plus 1 squared equals x squared. That's going to be 1 plus 1, which is 2, equals x squared, square root, and x equals radical 2. So I'm going to go radical 2, okay? And so these sides are the ratios that are always going to be the same on a 45, 45, 90. So the equation that we used in geometry was that the hypotenuse is always a leg times radical 2. So your hypotenuse is always a leg times radical 2. If this is a 1, it'd be 1 times radical 2. If this was a 4, it'd be 4 times radical 2. These ratios are always going to be the same for 30, 60, 90 and 45, 45, 90. So what you really want to know with your 30, 60, 90 are the equations. That's going to be helpful for you. But also these side lengths that lead to these ratios that are going to be the same over and over again, because this is going to help us out down the road. Okay? All right. We're going to come back to this here, I think, on this next slide. So we're skipping around. So this one is really going to help us out, I think, in lesson 4 when we get to the unit circle. But what you're going to want to have a general idea of is finding the exact values of these. Now, I'm not saying, hey, take out your calculator and go sine of 60, right, and hit equals, and you're going to write down 0.86602. No, that's not what we want. We want the exact value in terms of what we just talked about here. So what I'm going to do is, instead of going back and forth, is I'm going to draw these triangles again very quickly. Get this straightened out here for you. $30, 60, there's your 90. So this is going to be a 1, 2, this is radical 3, okay? And then my 45, 45, 90, 45, 45, and 90, 1, 1, and radical 2, okay? Excuse me. So, if I want the sine of 60 degrees, we're going to look at the little and here in the middle. We're going to take our 30, 60, 90, because here's, like, remember when we did above, we had the theta symbol for the angles? Well, now we have the angle, sine of 60. Okay, well, here's our 60. What does sine represent? Sine represents opposite over hypotenuse. So here's your 60. opposite over hypotenuse. So that would be radical 3 over 2. And you know when I said just 2 seconds ago, I said sine is 60, and you put it in your calculator, hit equals. Just remember that decimal. I should be able to go, if I went sine of, well, I won't do it that way because that'll just be a little bit more confusing. The point is this is what I want for your answer, radical 3 over 2. I want the ratio, okay? Cos of 45, well, then it means you go to your 45, 45, 90 triangle, and it doesn't matter if you use this 45 or this 45, it's the same. What does cosine represent? Cosine represents adjacent over hypotenuse, so that'd be 1 over radical 2. Now, when you put 1 over radical 2, we have to make sure that we rationalize the denominator. So when I'm asking for the exact value, don't put this down for an answer. We have to rationalize the denominator, which would be radical 2 over 2. So radical 2 over 2 would be the exact value. Same thing on tan of 30. The 30 tells you I got to use my 30, 60, 90 right triangle. I want the tangent at 30. So pencil goes on 30. What does tangent mean? Tangent means opposite over adjacent. Opposite 1 over adjacent radical 3. Same kind of situation, 1 over radical 3. We have to rationalize that denominator. So radical 3 over radical 3, which would be radical 3 over 3. So radical 3 over 3. That's what I mean by finding the exact values. Okay? So you got to start training your brain right now to be thinking about the 30, 60, 90 right triangle and the 45, 45, 90 right triangle. You should know that the long leg being 1, hypotenuse 2, radical 3 is opposite the 60. Likewise, the legs being 1 and 1 in radical 2, because those ratios are going to come into play over and over again. Okay? All right. I know this is a long set of notes, but this is for 1 and 2 here. So now we're going to just do some basic geo from and finding some side lengths and some angle measures as we go. So I'm going to put my right angle right here, and it says find the distance from point A to point B. So that's from here all the way to here. Don't know why that circle's there. Let's just call that x. So if we want to find x, we're going to use this angle right here of 65, and we're going to figure out what relationship the x and the 100 have to the 65. When I say relationship, I mean, are we talking sine? Are we talking cos? Are we talking tan? What relationship does it have with the 65? Well, here's the 65, so here's the focus point. Okay, so this would be the adjacent side would be 100 to 65. Here's your 90-degree angle, so that's going to be x, so that's the hypotenuse. So what's adjacent over hypotenuse of the 3? That's cosine. So we're going to go cos of 65 degrees equals adjacent, which is 100, over the hypotenuse, which is x. And now you have to solve this for x. A lot of different ways to do this. I always make this a proportion and cross multiply. Okay, so I'm going to go 1 times 100, which is 100, and I'm going to have the cos of 65 times x, and we need to solve for x, so we're going to divide by the cos of 65 on both sides. And so we take out our calculator, and we go 100 divided by cos of 65, and we hit equals, and we get x equals 236.2. So that distance from x is 236 feet. All right. Let's go down to the bottom example here. Again, we're finding lengths again, so you can tell that the angle is given to us. We need to find the height of the tree. So here's our 90-degree angle here. This is essentially what we have. We want to find x. So again, you locate the angle, and you ask yourself, what relationship is the 30 and the x with the 57? Are we using sine, cosine, and tangent? So 57 is here. It's touching 30, so that's the adjacent side. X is the opposite side, so what's opposite over adjacent? That would be tangent. So that tells you you're going to use tangent of the angle, 57 degrees, which is opposite x over adjacent, which is 30. So that's your setup. And again, I always make it a proportion and cross multiply. So 1 times x is x. And this time we just take tan of 57 times 30. Tan of 57 times that by 30. And that's going to give me 46.1. 46.2 if we're rounded to the nearest tens. Okay? All right, we're almost done here. Now, finding angle measures. So when we're finding angle measures, you may remember from geometry, we need to use inverse trig. Okay, so we're going to use these buttons, sine -1, cos -1, tan -1. Anytime you are going to find angle measures, you have to use inverse sine, inverse cos, inverse tangent. If you look at your calculator, if I get it to kind of zoom in there, you'll see your sine button here, cos and tan, and right above them, you'll see the sine -1, cos -1, tan -1. You want to use those functions to find angle measures. Now, the nice thing is the setup that we just did is almost identical. So if you look here, I see this x, okay? First thing I notice, I'm finding an angle measure that alerts me that I'm going to use one of these three. Now we just have to figure out which one we have to use. So again, what relationship does the 2.5 and the 5 have with the x? That's opposite 2.5 over the hypotenuse, which is 5. So what's opposite over hypotenuse? That's sine. So it's inverse sine of 2.5 over 5. Now, when you're doing angle measures, there's no equation to solve for. You don't like cross multiply like we did in the previous one. You just literally go second sine. So you see in your calculator it says sine -1, and you just type in 2.5 divided by 5. You hit equals, and you get 30 degrees. So x is going to be 30 degrees. Okay, that's all you do. Let's do this one down here at the bottom, finding angle measures. Again, I'm finding angle measures, so if I'm finding angle measures, that means inverse. Okay, here's my angle measure of x. What relationship do the sides have with x? That's opposite. This is the adjacent, so opposite over adjacent is inverse tangent, and it's 300 over 400. Again, when you're finding angles, there's no equation, there's no cross multiplying. You just literally just type it in your calculator. Second tan, 300 divided by 400, it equals, and I get the angle being basically 36.9. I'll round to the nearest tenth, so 36.9 degrees. Okay? I know it's a long video, but I wanted to try to give you as much review as I could without going too crazy. If you have questions in class and you want to go over some of those foundational trig functions and those ratios, again, we can do that in class, and I can show you some more proofs if you want to see where this stuff is being derived from. But I tried to show you that in the first couple slides with some of those side lengths. All right? I wish you the best of success when we start working on the assignment, and as always, if you have questions, I'll be happy to answer them. Take care.